All right. So hello, everyone. Welcome to the Climate Change AI webinar series. My name is Priya Donti, and I'm one of the co-founders and chairs of Climate Change AI, as well as an assistant professor at MIT. For those of you who are attending your first event from Climate Change AI is a nonprofit that fosters impactful work at the intersection of climate change and machine learning by providing education and infrastructure, community building, and advancing discourse in this area. CCAI conducts various initiatives to disseminate knowledge at the intersection of climate change and AI. So we offer digital resources, coordinate a range of events, including summer schools, conferences, workshops, webinars, and meetups. We provide grants to support the establishment of new work, and we're actively engaged in policy discussions to foster better policy initiatives. Additionally, we also bring together a vibrant community that stays informed through regular updates via our newsletter. And for more details, you can visit our website at climatechange.ai. In particular, we encourage you to join our community platform in order to connect with the wider community. By doing so, you'll gain access to valuable information from CCAI and have the opportunity to meet and engage with other people who are interested in various fields of application. We also have a blog that covers a wide range of topics, including research applications and presentations from the team. And if you're interested in what we do, you can follow us on Twitter or sign up for our newsletter, where you'll have access to updates about conferences, funding opportunities, recent projects, articles, job opportunities, various resources from around the space. So during this webinar, we'll start by having presentations from both of our speakers and then have some time for Q&A at the end. In order to make the webinar interactive, we really encourage you to ask questions, and we ask that you please connect to the associated Slido link. There's a QR code on the slide, and I'm guessing that the Slido link will also be dropped in the chat. And you'll be able to ask your questions on the Slido platform and upvote for your favorite ones. So the webinar will be, our two speakers will each have around 20 minutes to present, followed by, again, Q&A at the end. So please do add your questions into the slide and we'll process them as we go. So without further ado, I would love to introduce our speakers. So our first speaker will be Jingzhao Zhang, who is an assistant professor at the Institute for Interdisciplinary Information Sciences at Tsinghua University. He graduated in 2022 from the MIT EECS PhD program under the supervision of Prof. Ali Japari and Prof. Suvitra. Before that, he received his BS degree from UC Berkeley and was advised by Prof. Laura Waller. And his research focuses on providing theoretical justifications and analyses to practical large-scale optimization algorithms. He's also interested in machine learning applications, especially those involving dynamical system formulations. He received the Ernst A. Guillemin SM Thesis Award and George M. Sproul's PhD Thesis Award, which is fantastic. Our second speaker is Guanan He, who is an assistant professor at the College of Engineering at Peking University. He got his doctoral degree from Carnegie Mellon University in Engineering and Public Policy in 2019, alongside me, and Guanan was a really great PhD colleague to have in the program. And he also did his postdoctoral research at the Massachusetts Institute of Technology from 2019 to 2021. Guanan's research interests include machine learning and optimization of energy systems. He's published in journals including Nature Energy, Nature Communications, Joule, Energy and Environmental Science, and was an MIT Energy Fellow. So really two very impressive speakers here. And I would love to hand it off to both of you. Thanks so much for agreeing to present today.
Okay, thank you, Priya, very much for the introduction. So let me try to share my screen. Okay. All right, so is the slides presenting properly?
Yes, I can see them great.
Okay, great, thank you. Okay, so thank you all for being here. So I think so because we have a relatively small group of audience, so I would prefer, if there are any questions, please interrupt me at any time. So my name is Jing Zhao. I'm from Tsinghua University, and so today I'll present this work together with Guanan on a real-world dataset for estimating battery safety and capacity. Okay, so this work was done jointly with Yanan, Haowei, Benben, Shaobo, Wang Chen, Zhang Yang, Xuebing, Dongxue, and Minggao. So this is really a joint effort. So I am from a CS background, so I'm not a traditional energy researcher, but together with especially support from Guangnan, we are able to investigate this problem, which really gets me interested. And together we get support from Peking University and across different departments at Tsinghua, and also support from industry. So we have a large group of collaborators on this. And okay, so let's get started. All right, so I think this webinar is about AI in climate change. Okay, so but why is that related to battery? All right, so I think so the first point is so battery is very important for decarbonization for various regions. So first, there's we can use a battery to electrify transportations or vehicles, and that can reduce carbon emission, and also in order to integrate renewable energy or in order to integrate renewable energy into grids, we also need battery to stabilize the power system. And so there are also other reasons, such as the ones listed on this slide. Okay, so however, so battery is very important for reducing carbon emission and for helping with the climate change, but it also introduces new problems. So for example, in these slides, we can see that battery sometimes can cause unexpected fire incidents. Okay, so this not only happens for EVs, but also happens for storage systems. So the previous one was incidents by the electric vehicle, but this is also happens for well-managed storage system that are run by institutes. So these are real news. And aside from safety problems, so we are also interested in estimating the residual value in batteries, because we know that when battery run for something like 1,000 cycles, usually they are not as stable as before, and it's time for us to decide whether we should use them for some other purpose, or should we just decompose them and recycle the materials. And therefore, so for these two problems, these two new problems are introduced by the large-scale deployment of battery into the clean energy. And in general, we would like to solve two problems regarding the battery. So the first one is about estimating the safety, which means that we want to prevent fire incidents or unexpected failure ahead of time. And the second is that we want to estimate its capacity. Okay. However, estimating these two status are very difficult, and there are multiple reasons. So the first reason is that when we look at these battery systems in real world, their charging patterns are very diverse. Okay, so I'm presenting a figure here. So this is a collected EV battery real world data, and so we can see that although this is collected from a single vehicle and by a single owner, but we can see the charging pattern can vary largely, and the amplitude of the currents can also have very great variation. Okay, so that's one reason. And the second reason is that in real world, if we want to estimate the status of a deployed battery, we have very limited sensor information. So for example, if we want to decide how the battery inside a vehicle, electric vehicle is, then the only information we have is from its BMS system. And therefore, so many algorithms that requires more advanced sensors cannot be deployed in real world. And therefore, so that comes to our main topic. So we want to ask, so what can AI do for climate change? And so our perspective is that AI can help with predict battery safety status and can help with estimate battery capacity and its residual values. So that's our purpose. And so the question is, so why is AI good for this? And if we can look at a very simple problem for AI community right now, so which is to tell a dog from a cat from camera images. So this was not a very well solved problem until recently, until 10 years ago. And so the main problem was similar. So first, if we want to decide this, we only have limited sensory information. So we don't have how what is the shape of the animal, or how does it touch like. Okay, so we only have its the optical information. And second, so the information we collected are also noisy and diverse. Okay, so we have all these animals in different backgrounds, but AI could solve this. So therefore, we think there's a chance that AI can help us predict battery status and to determine its residual values. So that's our goal. And of course, we are not the first one to investigate this problem. And there are many works already. So we just have a very limited selection of two works here. So for example, this one was published in 2021, and it's used machine learning algorithm to determine the state of health of batteries. And we can see from the right plot that the prediction and the actual measured value correlates very well. Okay, so I can give another plot. Sorry that this figure didn't display very properly. But in the end, so the second plot is from another article published on Nature Energy. It's called Data-Driven Prediction of Battery Cycle Life before Capacity Degradation, if I remember correctly. And the idea is, can we use the first 200 cycle to predict how long the battery can last? Okay, so this is used to predict the residual value of a battery. And the takeaway from this work is that if you look at the right figure, so there are some very strong signal on how we can use early cycles to determine how long the battery could run. Okay, so it seems that we somehow have already solved these problems very well. Okay. However, I think so there is still could be a still big gap that for AI to do, and that gap is between the lab environment and real world setup. Okay, so all the previous data sets, or at least the two works I presented, were applied to data that is collected in lab environments instead of from real world data. And there could be a huge difference here. So for example, so the lab figure was a collection of battery records that is collected in the data in the lab. And so the color of the plot indicates how long the battery has run. Okay, and we can see from these figures that there is a very clear trend. If I want to determine which status the battery is, I can put it in context of other batteries, and then I will know that whether it's relatively old or relatively young. Okay. However, so the right figure is what we actually collected from real world, and this is the electric vehicle data. And again, so the color will indicate how long this battery has been used. And if we look at this, it is very hard for us to just look at the shape of the line or to determine a single easy feature to know whether this battery is at its end of life. Okay, so algorithm that was developed in lab setting cannot be very easily applied to real world setup. And that is the problem that we want to solve. Okay. So this is actually also a very important topic in AI research. And it's it's a central research topic actually. But so when Guana and I looked into this, we weren't able to find much research in energy-related AI algorithms. And the main reason is because very little data is publicly available about real-world battery operation records. So the closest I could find was this one. So this was actually, I was able to find this year, but this was already 2023. And it says if we want to improve EV batteries, we should study them on the road. And I totally agree with this. But again, so this is, this data set was released recently as the same time as we did. But so the data set is very different. And okay, so the difference is because of this released data sets was again also collected in lab environments. Anyway, so this is our purpose. So we haven't really talked about how we solve this problem, but if we think from the perspective of AI research, the starting points a researcher would do actually is to collect and release the data set so that people can start thinking about it and to think about how should we formulate this and how should we benchmark all the algorithm. And that's our goal. And also, so why we release this work. Okay. And therefore, so this gets to our first work. So this work has not been accepted yet by AI conference because I think people do not think that this data set is very different from other time series anomaly detection algorithm. But we believe that this is very important for its practical value because it's trying to solve a real world problem. And so aside from this work, so Guangnan would also present another work that is published, which we will introduce later. Okay, but anyway, so this work is a manuscript that describes a real-world data set, and it's available through arXiv. Because it's not published, therefore we will keep polishing it, and we will have the latest version at this arXiv link. Okay, so let me just describe the data set directly. So what does this data set contain? So first is a collection of time series. Each time series have a fixed length of 128, and that corresponds to 2 minutes of charging records for a battery. And so each snippet has 6 features, and these features are usually available through protocols provided by BMS system. And so therefore, we were able to collect all these data from real world EV across China. So how many of these snippets do we have? So I think this is actually the largest data set I could find online. So we have 3 data sets in total. And so each data set have something from 200 to around 50 vehicles. And each vehicle run from roughly 3 months to 3 years. And depending on how often they charge the battery, so the number of charging snippets can be found, are listed in the table. Okay, so we have in total roughly 1 million charging snippets. Each snippet lasts for 2 minutes. Okay, so that's roughly the size of the data set. And so along with all these records, we want to provide labels. That's another thing that AI algorithm will care about. So we need labels in order to train our models. We also need labels in order to evaluate known algorithms. So for these data sets, we released two types of labels. So the first label is called anomaly label. So anomaly label reflects the safety status of a battery. And in particular, so we say that a vehicle is abnormal if the data provider receives fire or lithium plating reports sometimes in future. Okay. So these labels are actual real labels, but we were not able to guarantee that the normal vehicle will not cause any incidents in future. But the abnormal ones, at least we received reports. Okay. And so another label is called capacity label. So this corresponds to the second task that we described for battery. So we said that so for battery, we care about 2 problems. So one is safety, and the other is residual value. And one thing that is important or critical to determine the residual value is how much capacity can be charged into the battery during one charging cycle. And so these capacity labels, in contrast to the previous normal labels, are actually labeled by algorithms because we are not able to get the EV back and to charge them from 0 to 100%. So I can give some high-level idea on how we label the capacity and its limitations. So the way we do it is not directly using the OCV table provided by the BMS system. So instead, we would cluster each charging snippet according to its environment. So such as what is the average current that is used to charge the vehicle, or what is the temperature, because these two are the 2 major factors that would determine, even though the battery is the same, it will charge a different amount of ampere hour according to different working environments. Okay, so we would cluster them according to these environments. And next, so for snippets that are in the same environments and are also close to each other, we can connect them to get longer snippets. And therefore, so we can use a more stabilized OCV table to determine what is the capacity in it. And we can, so the effect can be represented by the figure here. So on the left one, that is the label provided by our algorithm. And on the right one, that is the standard OCV SOC estimation. And we can see that it's more stable. However, so the limitation is, of course, that we cannot provide a capacity label for every snippet because some of them are too short, or some of them do not have adjacent snippets in the same environments. Okay, so this is how we generated the capacity labels. Okay, so with these two labels, we have some initial attempts on how known algorithm can work in helping with solving the battery safety and capacity estimation task. Okay, so the first thing that we tried is, so how would known deep learning based anomaly detection algorithm, so that is what AD stands for, anomaly detection algorithm work for these data sets. And if we remember, so the anomaly label were mainly provided for two data sets, so battery data set 1 and battery data set 3. And in this table, we have 5 algorithms. So all these 5 algorithms are very famous or well-known deep learning anomaly algorithms. And we apply to them, and we can see that the AUROC, which is a measure for reflecting how accurate our prediction or our estimation of the anomaly is. And so the best one would be 100%, but in general, we get something around 60%, which is quite low. Okay, so this is far from satisfactory, but we think this is not a bad news, because this only means that our implementation of general anomaly detection algorithm did not work very well. And this will motivate us to design models and algorithms that are tailored for this particular task, which is actually the central topic that Guannan will present later. Okay, so aside from anomaly labels, we also have capacity labels. So for capacity labels, we run some more famous and the standard baseline. And our goal is not to say that we provide the best algorithm for this task than other works, but we just want to run and see how well this easy baseline perform. And we can see, so we have some very famous models like random forest or MLP or LSTM. And actually, so for capacity, it seems like this precision represented as RMSE is much more accurate and is within is acceptable. Okay, so but we didn't. So as we stated here, so we avoided models that are designed specifically for batteries because we cannot very easily find public code, and we are worried that we cannot properly implement the pipeline. Okay. Anyway, so these are the data sets. So we have 3 data sets in total, and we are still working on in pre-processing and cleaning more data, and we may release them on the archive link that we provided before. And so with all these data sets, our goal are threefold. So first, we want to initiate the process of making battery AI public and open source. Okay, second, we want to facilitate interdisciplinary research, because without data, it is very hard for AI researcher to work on this topic. And so last, so we want to, in the end, develop AI models that can be deployed in the real world. And so regarding the third point, Guannan will present our next work.
Okay, good. Thanks, Jinzhao. And so In the following, I will present our recent work published on Nature Communications that use the data set Jinzhao just introduced. The task is on the fault detection of lithium batteries in electric vehicles. So in this work, our goal is to predict the battery fault with only battery management system data without additional sensors. We do not consider them because they might be costly and they are not ready in commercial use. So the main challenge in battery fault detection with our data, we have both normal and abnormal EV labels. The main challenge is that they are poorly differentiated only with common features. That we cannot use very simple features to predict them. So we can come up normally with the variance in cell voltage, current, or temperature. So in this figure, we plot the distribution, or say the frequency of the variance in cell voltage, the current, and the temperature. We show the mean temperature and the max temperature. So there's no obvious pattern difference between the normal and the abnormal distributions. The blue ones are normal, the red ones are abnormal vehicles. And we also calculated the area under the receiver operating characteristic, or say the AUC or AUROC, which is a common indicator of the whether the algorithm is effective. So higher values indicate greater power. So the AUROC of the variance is very low. It's only around 0.5, which is the same as the random guess. So we have also tried other statistics, but none of them works very well. So here's a detailed plot of the lithium batteries charging snippets from two sampled EVs, one with fault, the other without fault. There's no simple features to detect the difference. This is because the fault mechanisms are very complex, involving hundreds of reactions. The other challenge is that sometimes very rare charging patterns may cause the algorithm to have high false positive rates. So we have so when you have a car, so normally you don't use fast charging because you can park it at your home and charge it overnight. But sometimes you need to fully recharge your car very soon, like you are having a very long trip. You need to use a highway fast charging station. So at this situation, most algorithms will detect the fast charging as an anomaly because it normally learns of distribution over the data, the input data, and tend to detect such infrequent fast charging data as anomaly. So this will result in very high false positive rates for normal algorithm. And we talked to battery manufacturing companies. They keep telling us that they don't want high false positive rates because that means a lot of costs for inspection for them. So to address this problem, we develop a deep learning model, and we call it DYnamical autoencoder for anomaly detection, DyAD. So it's the first deep learning model tailored, specifically tailored for large-scale real-world EV battery, lithium battery data for anomaly detection. And we designed it to be privacy friendly, which is important for car owner, and also for the algorithm for the car manufacturer, because sometimes they also want their algorithm to be private, and it's communication efficient. We use a hidden Markov model of battery data in designing such a neural network pipeline. And so we also try to balance the lithium-ion battery accident costs against the inspection costs with the parameter tuning, and also using the empirical statistics of like the base fault rate of EV battery. So this is the deployment scheme chart. So we in the real world, we have charging station, we have a EV fleet, we also have a cloud platform or server, like the who owns the algorithm and provides us such server as SaaS. So with the charging station, it collects BMS data, and it transmits such data after encoding. So we have an encoder network at the charging station. After encoding, it transmits the data to the cloud server. Then the cloud server has a decoder network. It generates a fault score based on the reconstruction loss and the other loss. Then it also collects a lot of social and financial statistics about the cause of inspection, the cause of accident, and the base fault rate, and it makes decisions of whether it sends a fault signal to the EV fleet and to send people to inspect the car. So this is our framework. As we said, so traditional deep learning algorithms detect the anomalies by learning a distribution. So infrequent like fast charging data points are likely to be detected as a fault. So such logic is problematic. So we propose a dynamic autoencoder to address this problem of to be adaptive to the real current pattern. So the dynamic autoencoder, it's also adopts an encoder decoder structure, but the decoder here we maps the inputs, maps the decoder system response from the system input. So we model the physical system. So the intuition behind the structure is that we view the lithium-ion battery data as collected from random nonlinear dynamical systems. So we do not just find the problem of the data. We do not just detect real data. We detect the problem, the real events of the system, the dynamical system. So that's why we name it as a dynamic autoencoder. So this is a simple graph that shows the difference. In the traditional vanilla autoencoder, it learns encodes the input and then decodes the input from the latent variables. So this is how they calculate the reconstruction loss. In our framework, we also decode the latent variables for with the system input as an input of the decoder. So this makes the autoencoder learns the dynamics of the system. It learns the response of the system from the inputs. So this framework is better tailored for anomaly detection of dynamical systems, not just battery systems, maybe also other energy technologies that has such dynamical insights. So we update our neural network parameters by minimizing total training loss with 3 parts. The first part is reconstruction loss. Second part of the mileage supervision. So we use the mileage of the car as a weak supervision. The third is a common pair regularization loss. And so we split our BMS data, the data from the battery management system, into two groups. One group is the system inputs, which includes the current, the state of charge, and the other group are the system response, which are the voltage and the temperature. So then the encoder maps the inputs into the latent variables, and then into latent variable. Then the decoder then represents the decoder maps the latent variables and takes the system input as the input to the system's response. So our latent variables represent the system, the dynamical system's parameters, and our model then detects system anomaly based on the difference between the reconstructed system response and the observed system response. As we said, we also add the mileage as another loss to help the anomaly detection process as a weak supervision. Another problem for lithium EV battery data is that the abnormal vehicle labels are very sparse, and it's all only available at the vehicle level. So if you have a car and you find that it has a fault, the battery does not work, and you send it to the car, back to the car manufacturer, it will only know that your car has a problem. Sometimes the manufacturer can open the battery pack, but you do not really know which cell causes the initial problem. So that's why we only have the abnormal labels at the vehicle level. Therefore, these labels may not be very helpful to reflect the condition of each data point, which is at the cell level. So we do not really know which particular charging snippet is problematic. To address this, we use a robust scoring procedure to generate vehicle level predictions from charging snippet predictions. So we parameterize the whole procedure by hyperparameters tau and p, which predicts whether a charging snippet is abnormal by thresholding the reconstruction error at value tau, and we predict whether a vehicle is abnormal by averaging the top p percentage of the errors. So both tau and p are hyperparameters, and we fine-tune them on the training data set. Then, based on the charging snippets data, we can predict whether a vehicle is normal or abnormal. So in our experiments, we use the data set that Jinzhao just introduced. Normally, each snippet has 128 time steps. The time step is every 10 seconds, and so the total horizon is about 20 minutes. And we only use charging data at least some months before a car battery was found abnormal, so that we can predict the fault long time enough before it gets problem. And we use bifold evaluation. We split the data into training and validation. So 4 normal, 5 normal groups and 5 abnormal groups. 4 abnormal and 1 abnormal group are used for training. The other 1 and 4, 1 normal group and 4 abnormal groups are used for testing. So here are the results. We compare our proposed dynamic autoencoder algorithms with other deep learning baselines, and also the very standard non-deep learning one, which we call the variation evaluation method. The variation evaluation method use some like the variation in the voltage, the temperature, the resistance, the capacity, and also other very common car data. We evaluate the variation and then use the average, weighted average as an indicator. So this is a non-deep learning ones. The others baselines are deep learning ones with different neural network structures behind. So we found that our proposed DyAD, which is a red curve, improves the ROC curves over the state-of-the-art algorithms. The other, the uncertainty here, the bound here, are from our 5-fold evaluation. So the improvement is about 16% to 63%. We also calculate the AURC, the area under the ROC curve. We found that our algorithm improves the AURC by a very huge amount. And we also calculate our average direct cost of the from the fault of EV batteries. It consists of the cost of inspection and fault. We found that it lowered the average direct cost by over 33% compared to other baselines. So here, the left is very commonly false positive vehicles by other baselines, but it's correctly classified by our algorithm. The right one is commonly false negative ones, which is it has fault, but it's not detected. Then it's also correctly classified by our algorithm. So here, how we calculate the direct cost. We take a fault, cost from fault and cost from inspection. We calculate the total expected direct cost using the fault rate, and also the true positive and false positive rate of our algorithm, and also other baselines, deep learning baselines algorithms. We found we plot the total direct cost for different algorithms here, so in some areas, the fault cost may be very high. In some areas, the inspection cost may be higher. So we classified into 4 scenarios: low fault cost, high inspection cost, low and high fault cost, low inspection cost, and high and both low fault and inspection cost and high cost. So we found for all scenarios, the total expected direct cost first decrease, then increase. And this optimal true positive rate, which is about 50% in this application. So, and our algorithm reduces the expected direct cost by 33% compared with deep learning ones, and 40% compared with the non-deep learning one, which is the variation evaluation algorithm. And we also test the algorithm with different base fault rates, which turns out that our algorithms also have better performance in different scenarios. And here we show how the proposed algorithm work by showing how abnormal and normal snippets are separated in the output layer. So in the input layer, so this is our input data without encoder and decoder, without encoding and decoding. So we cannot, the red one and the orange ones are normal and abnormal data for one EV, and they are together very close to each other. We cannot really tell from them based on this plot. And in the latent variables, latent variable layer, they are also jumbled together. But in our output layer, so the red one and the orange ones, the normal and abnormal data are separated. And we also plotted some example data with the features that we can use to predict the force. So we can use some features with real physical meanings to make a prediction. But it does not always happen. So we just chose some data that can be predicted by those features. For the others, you cannot use those features to predict. So we found that some features like the prediction errors of temperature and voltage, like the reconstructed difference between the temperature and the voltage, can be used to predict. So here we show, we select the 3 snippets from the one EV, and so we found the predicted and observed temperature and voltage are very high, and then you tend to predict them to be problematic. So here a summary, we have released 3 data sets of batteries with snippets, and we propose a dynamic autoencoder for lithium-ion battery anomaly detections. And we have shown that they are effective over existing deep learning and non-deep learning ones. And so we call for benchmarks for AI applications in climate change research, and so they are very important for use of AI algorithms, not just AI for climate change for batteries, but also other fields. So thanks again for our collaborators in Tsinghua and Peking universities, and yeah, that's all. And we are happy to answer any questions.
Fantastic. Jingzhao and Guanan, thank you so much for these really interesting presentations. And for those in the audience, remember, you can ask questions via the Slido, which we'll then relay to the speakers. So we have several questions. So first of all, so this is for both of you. You again mentioned, I think, this really important aspect that, data collected in the lab about batteries is, very different than kind of real world charging data sets. Could you talk a bit about, what the implications are of, if you try to use an algorithm that was developed on a lab data set, but actually deployed in the real world? Like, what can go wrong, actually?
Sure. Thank you, Priya. So I think so. If we take a machine learning or AI class, so the first thing we learn, the first important concept we learn is about generalization error. So generalization error says, so how much would change if I apply my algorithm to train data versus test data. And so similar thing will happen if we deploy the model from lab setting to a real world setting. So this arrow would appear in the sense that, so for example, we may predict 1% of the vehicle as abnormal in lab setting. But when we apply them to real world, maybe that number increased to 5%, which seems okay. But if you really want to deploy this model, then 5% is too high to record the vehicles. So therefore, so I think that what breaks is that we need to take real world constraints into account while we design these algorithms, and we want to design algorithms such that its feature is invariant to this change of distribution. Okay, and that is, I think that is the central challenge for designing AI algorithms.
Yeah, and that totally makes sense. This idea of kind of distribution shift is really difficult. Concretely, though, kind of what actually ends up being different between the lab and the real world data set? So, you know, what are the practically, like, what are the specific things that tend to that the lab data sets really tend to miss that you start to see in the real world data sets?
Okay, so I think the major cost, the cost for the difference is that when you collect data in lab setting, you have limited resources. I need students to supervise the collecting procedure. I need to design the charging protocol. But in real world, so these variations are natural and millions. So different people, like, they can charge the car and then leave in half an hour or sometimes in an hour. But in lab, you have to have a standard procedure for that. And also the environments, the temperature, the charging station, like, so they are all different in different cities. But in lab, we only have one set of experiments. So that therefore, so the data collected in lab is necessarily less diverse. Yeah,
no, that definitely makes sense. Thank you so much.
Sure.
So there's a question here also for Jingzhao, which is, how was the time horizon of each snippet chosen? So was it 20 minutes? And then how does that affect what kinds of analyses can be done on the data set?
The horizon, sorry, I think I made a mistake during the presentation. So in this data set, so each snippet lasts for 20 minutes, not 2 minutes.
Yep.
Okay. Yeah.
And and how was that length chosen? Yeah.
So okay, so that 20 minutes was chosen mainly because the charging protocol usually lasts from 20 minutes to something like several hours. So we picked this shortest time window, and then we chop them so that they can be fed into standard time series models. But yeah, we also chop them because to do anonymization, because somehow we want to break and make the data less ordered, so that we do not release the owner information.
Yeah, that makes a lot of sense. And how do you think that choice of 20-minute snippets kind of affects what kinds of analyses can be done on the data set versus, you know, what might not be able to be seen in the data set?
Yeah, I think if you use a longer time window, it's possible to design better algorithms. So if we figure out a way to clean data in that way, we will do that. But at least until now, we were not able to find such algorithm ourselves. But we would like to invite research in this, and if we are inspired, or if there's strong interest or idea on how we can release longer data without releasing the entire charging information, we would do that.
Yeah, definitely. I feel like that aspect of you know, what makes sense algorithmically and also contending with privacy considerations when it comes to personal data sets like this. I feel like it must be a huge challenge. And so maybe relatedly, were there any kind of, what were the most challenging parts of actually constructing this data set? And what advice would you give to others who are trying to construct similar real world data sets?
So okay, so I can give my perspective, and maybe Guanan could give his perspective. So for us, so one thing is, so of course the manufacturer will not be happy to release the data, so they don't have incentive to do this. Okay, so we have incentive to, we could do this because so we are collaborating and representing our research group, and we show them how we clean the data, and we show them what the cleaned data look like, and so that we can convince them that no sensitive information is released. And so for me, that's that could be time consuming and that can be require a lot of care and to be patient. Okay.
Yeah, thank you. And Guanan, do you have any perspectives on that question as well?
I think battery data sharing and circling are very important. Like there are tons of battery data deposited at the platforms of battery manufacturers, and most of them are not fully exploited. So even there are many battery manufacturers, if they are willing to share their data between them, among them, so they can also have higher social produce higher social welfare. Like even both for battery electric vehicles and for the stationary energy storage, and so I think there needs to be a mechanism to incentive them to share, and maybe a pricing mechanism to determine the value of a data set, and so that they are willing to produce value using them. Yeah.
Yeah, no, that makes a lot of sense. Thank you. Guanan had a question on your part of the presentation. So I think you started to get at this when you were showing the clustering of features in latent space, but I think you mentioned early on in the presentation that, good versus anomalous batteries are not distinguishable via standard features. Would you say that's sort of the main reason why standard anomaly detection failed, or are there other reasons? And then sort of how does your method fix those reasons for failure of standard anomaly detection methods?
Thank you, Priya. So this is so we have we have two main courses for preparing this new anomaly detection algorithm. One is that the common features, like commonly used statistics, cannot predict the fault or the anomaly very well. We show that either the variation the evaluation method has been very commonly used in manufacture so these are based on feature but yeah, they fail. The other is that existing deep learning ones or data-driven ones that does not use the features, they also fail to some extent, especially about the real charging pattern that I just talked about. So the features with physical meanings cannot really be used to find the latent variables that are or very complex mechanisms that interact with each other. This one. Second, the sparse behavior and the lack of a lot of vehicle labels so make us to introduce this new algorithm. Yeah.
Awesome. Thank you for spelling that out. That's super helpful. And I guess a sort of question along similar lines, which parts of your algorithmic pipeline do you think had the biggest effect on performance? So you talked about, different architecture, you talked about your loss function. Which of these do you feel like was actually the most important maybe in achieving some of these performance benefits?
The main contribution is the structure that we put the input, including the current and the state of charge into as an input to the decoder. So it does not learn a distribution over the data, but it learns a response of the system. So this tackles the problem of the real charging patterns. So this is also a difference between the lab data and the real world data. In lab data, for each protocol that you have some data, you normally have the same number of data over different charging protocols. But in real world, that you do not. You have a lot of you have much more, like 90 over 95% of data which are normal charging, but very few percentage of fast charging or at some extreme temperatures. So these are the main problem of using lab data-based algorithm. So these algorithms might work for lab data, but not really for real-world data.
Yeah, no, that makes a lot of sense. Thank you. So we're towards the end of time. So I just want to close. Last question being, are there any kind of key takeaways or kind of, major last points that you'd like to make sure to share with the audience?
So Jinja, you want to go first?
Yeah, so for me is so I think I mostly work on theory before, but for me it's looking into a real world problem is very exciting to me. So I hope that I would like to get more interactive with energy researchers, and I hope to get new perspective. And if you have any ideas or any interest in our projects, so please feel free to contact us.
So my takeaway, so it might also Jinzhao talked a lot to me about whether it's hard for AI scientists to get involved in batteries related research or other climate change areas. Is that the lack of benchmarks and data sets. Like we have some image identification data sets and competition for a long time, but for batteries and climate change areas, they're not much more than those typical data AI tasks. So for our community, maybe we should call for more standard benchmark and data set and competition to foster collaboration. Yeah.
Definitely agreed. I think that, yeah, this idea of just standard benchmark data sets that allow more people to engage with these kinds of problems are so important. And so thank you both so much for putting this data set out there and for sharing your wonderful presentations with us. And thanks to everyone who attended the webinar. Our next webinar is going to be on December 5th, which will be a panel discussion on forest monitoring for carbon stock estimation. So we look forward to you joining there. And again, thanks so much, Jingzhao and Guanan, for your great presentations.
Thank you.
Thank you.
Bye-bye.
Bye-bye.